Okay, so thank you for the organizers, and thank you for inviting me here to give the talk. So I'm going to talk about the uniqueness of the welding problem for SLE and UV quantum gravity. And this is a joint work with Oliver Antigard and Jason Miller, who are here. And is it working? Yeah. Okay. So I start by the introduction. So we are interested in the conformal welding problem. So here we are given two unit disks, D1 and D2, and also a homeomorphism phi from the boundary of D1 to the boundary of D2. And we want to glue together these two disks so that their boundaries are identified with respect to this phi. So more precisely, we would have two conformal maps, psi1 and psi2, from respectively from D1 and D2 to the Riemann sphere, so that their interface is a loop such that the psi2 minus 1 composed with psi1 is exactly this homeomorphism phi. So this conformal welding problem, first we need to ask, does such a conformal welding exist when we are given such a phi? And also the second question is, if it does, then is it unique? So, and this is also, of course it is unique up to conformal automorphism from the Riemann sphere to itself. And so this is also the same as saying that the curve eta is removable, meaning that if I have any homeomorphism from the Riemann sphere to itself that is conformal in the complement of eta, then it must be conformal everywhere. This is a definition of saying eta is removable, so this conformal welding problem has a unique solution. So from 2010, Sheffield looked at the conformal welding problem of random surfaces. So he looks at the welding of two quantum surfaces, so that interface is a SLE curve. So here, quantum surface is just a normal surface with extra UV quantum gravity structure on top of it. So here, for example, if we have D1 and D2 and both with two marked points, and then we have a way of identifying their boundary lengths according to the quantum length, then we can glue them together so that interface is SLE curve. And in fact, in this picture, once we just glue one part of it, then we have the upper half plane, but we can then continue to glue the left and right part of the real line. So this is the quantum zipper of Sheffield's paper. And in that paper, this is defined for, so the uniqueness for this kind of welding problem is only known for kappa smaller than 4, because the complement of SLE kappa, when kappa is smaller than 4, is known to be a Holder domain due to Rode and Schramm, and this implies that it is removable by a result of Jones and Smirnov. And so then later in 2014, Duplantier, Miller, and Sheffield, in their paper, Liouville quantum gravity as a mating of trees, they defined the conformal welding for kappa between 4 and 8. And they say there is a unique way to weld together two loop trees. Okay, on the left it's a welding of just two quantum surfaces, but on the right it's a welding of the two loop trees, so that their interface is SLE kappa, which is self-touching. So this here there are in fact infinitely many connected components. So but this uniqueness is less than saying the curve is removable, of course, because they have a certain way of gluing the trees. And then, so the welding problem is not yet well defined for kappa equal to 4, and this is also related to the open question of whether SLE4 is removable. And so let me state our main result. So for any kappa between 0 and 8, so let eta be a SLE kappa curve in the upper half plane from 0 to infinity. And suppose we have a phi homeomorphism, which is conformal on the complement of eta, and such that the image by phi of the curve eta is also a SLE kappa curve. Then we show that phi is almost surely conformal everywhere on H. So this result gives us the uniqueness, like with, so it's not removability because we have this additional assumption that this image phi eta is also distributed like SLE curve, but it still gives the uniqueness of for the welding problem, and so in fact, So in fact, this result, it is a consequence of a more general result that I'll present now. And this more general result, in fact, it is a purely deterministic result that gives you some geometric conditions on the curve eta and phi eta, so that any homeomorphism phi that is conformal of eta must be conformal everywhere. So here I just impose eta to satisfy some condition H1 that I'll describe, and phi eta to satisfy some condition H2. And also this curve should have upper Minkowski dimension less than 2, which is a very reasonable assumption. Okay, so here the hypothesis H1 is just saying if I fix some compact K and some parameter any beta smaller than 1, I look at the annulus centered at some point inside K of radius epsilon beta to epsilon, and look at the number of crossings of the curve across this annulus, and it is always, there is some constant m that this number of crossing is always less than m. And typically this kind of condition is satisfied by like all non-space fitting SLEs. And the condition 2 is that, so for I fix K and the parameters alpha psi, and if I take delta 0 small enough, so I look at a point eta t on the curve, I look at a disk of radius delta around it, so here I zoom in this disk, I look at this red part of the excursion. It's actually just the curve starting from eta t to continue until the first time it hits this circle of radius delta, and also look at the last time before t that it hits the circle, this red part of the excursion of this curve. So we can find some ball by delta alpha that doesn't intersect eta. And also, this ball is very close to this red part of the curve, but much further away from any other part of eta which is inside this disk. So this condition is basically saying that this curve is not self-chasing. So if I give you some excursion, then the past and future, they are not constantly like chasing this curve, so that we can find some ball which is much closer to this curve. And this type of condition is also typically should be satisfied by any kind of non-space filling SLE curves. So with these two, so as I said, it should work for any type of such SLE curves. So for SLE kappa rho, CLE, and all the more exotic SLE kappa beta rho, a boundary CLE that, so Miller, Sheffield, Werner define. And so, but one particular result is just this gives us a uniqueness for the welding problem for kappa equal to 4. So actually the existence part, it's not formally written, but to define the welding problem for kappa equal to 4, the difficulty is in the uniqueness, because the existence parts, it's just because the critically weak quantum gravity has a slightly different renormalization. This wasn't written in the Scott's paper, but it should work in the same way. So if we believe in that part, then it gives you that this critical welding is well defined. It also, so since it also works for kappa between 4 and 8, it gives us a new proof of the uniqueness of the welding problem, and this uniqueness is stronger than the uniqueness in the sense of mating of trees, because for example, for the mating of trees, they have a way of gluing which is from one side to the other. So if you reverse this gluing, you don't know if you get the same curve. But for us, it says as long as the law of the curve is SLE, then you always get the same curve. Okay. So now I will talk about the proof of the theorems. And the nice part of the proof is that it doesn't really involve involve Liouville quantum gravity at all. And there is first part of the proof is about this theorem 2, which is about uniqueness for deterministic curves. So it doesn't involve SLE or other probability knowledge. And the second part is just to check that SLE kappa satisfies H1 and H2. And this is just analyzed on SLE. And maybe due to the time, I'll focus on the first part of the proof. Okay, so our proof uses this ACL property, which says in order to prove some function phi is conformal everywhere, we need to prove that it is absolutely continuous on almost every line, which is parallel to coordinate axis. This is a sufficient condition. So how do we prove that? We just take some line L, some horizontal line, and saying that it is absolutely continuous is saying that if we take any interval I, so the blue interval, and for every epsilon, the x delta, such that if I take any k and any 2k points and look such that the total length of these intervals xj, yj is smaller than delta, then the variation of phi on these intervals is smaller than epsilon. So this is a definition of phi being absolutely continuous. And to prove this, we need to control two different quantities. There are some intervals that do not intersect the curve, and some other intervals that intersect this red curve. So for the intervals that do not intersect eta, it is easy to control their contribution. We just Okay, yeah, so there's a small mistake, but anyway, we need just to do the Cauchy-Schwarz inequality for phi integral phi prime. There should also be an area of k here, and this is equal to the area due to the coordinate change formula, and this is finite. So phi prime is L1, so whenever I have the intervals with small length, then the variation phi is small. Now, so the rest of part is to control the variation of phi of the phi on intervals that do cross the curve. So to prove that, we will it is enough to prove this proposition. So we fix any compact rectangle K and choose Z uniformly randomly in K, and we will show that if we look at a small ball around Z that intersects the curve, then its expected diameter is of the order of epsilon to the 3 minus d minus this iota, which can be made as close to 0 as possible. So once we have this proposition, then this implies that the variation phi of intervals across theta is small. I'm not going to show the proofs, but the idea is we can subdivide this interval into small intervals of size epsilon. So there is a 1 over epsilon number of intervals, and since the expected diameter is of this order, so we get this big O of epsilon 2 minus d of diameter for the image, and since d is smaller than 2, then this is goes to 0, and so that's so now the rest of the talk I'll try to prove this proposition 3. Yeah. So here, so I will spend some time on this slide to explain. So why condition H1 and H2 imply this proposition 3. So here on the left part, it's a curve eta, and we assume that it satisfies condition H1, which means if I take the Z and two circles epsilon s beta, the number of crossings between these two circles is bounded. And so here I just draw 3 different excursions. And then on the right, so what we do is we just pick one excursion and map it to the right. Okay, actually this should be all red onto the circle. So we can find, we pick any point on this red part and make a circle. And by hypothesis 2, we can find some ball here which is much closer to the red part than to any other part of the curve. And now we want to show that the pre-image of this gray ball, it is contained in this ball of circle epsilon rho. So this kind of says that the image. So the final goal here is to show that the image of this ball is kind of close to being round, because if this is the diameter of here delta 1 is the diameter of the image of this excursion E1, And inside this ball, we can find some smaller ball, which is of diameter delta 1 to some power alpha. Alpha is bigger than 1, but can be as close to 1 as possible. So it's kind of saying that the image is close to being round. And so in fact, this is true because since this ball is much closer to the red part, if I start a Brownian motion from this ball, then it is much more likely to hit the red part before it hits any other this gray part of the curve. So this means its pre-image, a Brownian motion started from there, is also much likely to hit the red part than any other part of the curve. So that's why it cannot be too far away. So it must be contained here. This is just for one excursion, but we will also show that this, in fact, the diameter of this ball of radius epsilon, it is also comparable to the diameter, or at least smaller than the diameter of any of these excursions. It's because if you start a Brownian motion from this circle, it's much more likely to stop in these excursions than any part of the curve. So the image, it's also, the image of this ball of epsilon is also just can't be much larger than the image of these excursions. Yeah, so the result is that, yeah, you can always find such a ball which is containing the image of this this epsilon rho ball. Okay, and now using this result, we are now ready to prove proposition 3. Right. So we, in fact, in proposition 3, we said we randomly pick some z. The statement is here. We randomly pick some z in some compact set K, and we will show that the expected diameter is of this order. So here we will define this set ER epsilon to be the set of all z such that the diameter of the image of this ball BZ epsilon is of order epsilon to the power of r. And we only need to consider for r smaller than 1 because that's when because we want an upper bound for the diameter. So r bigger than 1 is not interesting. Then we want now it is enough to control the area of this set ER epsilon, and we will show it is of this order. So here I have a ball and its image, which is epsilon r. And by the previous result, we know that we can find we can find a ball of order epsilon to the r alpha, which is contained in this image. And also this ball of alpha is very close to the red part. So if you take a larger ball of epsilon r gamma, then it will intersect this curve. And now it doesn't cost anything to center these balls on some lattice. And then we claim that we look at this set YR, which is the number of Y that are centered on this lattice, and such that if we draw a ball circle of R gamma, then it does intersect the curve, and the total number of such balls in this set YR is just of the order epsilon to the minus RD, because typically alpha, gamma, and z's can be as close to 1 as possible. This is due to the dimension assumption on the curve. And then we claim that the union of all these balls, if we take the preimage of Y and draw a ball of circle of radius epsilon, then it will cover this set epsilon r epsilon, ER epsilon. So this is because this ball is in the preimage of this circle, so it will cover this point Z. Okay, so this means this area of this ER epsilon will be less than epsilon squared times the number of points in YR, which is of the order epsilon 2 minus RD. Yeah. And so then with this area estimate, we can now prove proposition that I stated before. We pick some Z uniform running in K and look at the expected diameter of phi b Z epsilon, and this will become integral of R from 0 to 1 of epsilon R to the area of this set, which is the integral of this order. And the order of this integral is just the maximum of R from 0 to 1 of this quantity. And since D is always greater than 1, this is equal to, finally, to get O of epsilon 3 minus D. And since D is smaller than 2, and so we are done with the proof of proposition. And we get, we prove this theorem about the deterministic curve. Okay, so actually, so this, okay, I can run ahead of time. Maybe how much time is?
You still have
15 minutes. Okay, because last time I gave this talk, I used 45 minutes, but since it's the second time, now maybe I forgot to say something in the middle. Okay, so I can. Okay, so this is the first part of the proof. So I can either talk about then checking SLE satisfies this condition H1, H2. Okay, so then I have to do it on the blackboard because I didn't. Yeah.
Just a question before you move on. So,
yeah.
So the trick is to look for this ACL condition.
Yeah.
So
yeah.
The basic thing is, say, if you have the ACL condition plus some one mild thing, then you know that you're quasi-conformal. That's the idea. And then because you're conformal outside of the curve and quasi-conformal on the curve, that's enough to get conformal everywhere. Is that the idea, or is it, how does it work?
So there is the condition that as long as you have ACL and you are conformal away from the curve, yes, then you are conformal everywhere. So yeah. Are you asking about?
Yeah. So that's the. Yeah. That's a sort of that's a known.
Yeah, that's a known fact.
Because then you are going to be quasi-conformal also, yeah, on the something like that.
Yeah.
You have the constant is 1.
Yeah.
Yeah.
Okay.
Yeah.
Okay.
Okay, so that's a known fact. Okay, so this is. So first, if you have any other questions, I can spend some more time. But so otherwise, I can just do the second part of the proof, which is to check that SLE kappa satisfy H1 and H2. And this, so the hypothesis H1 is actually very easy to check. It's just because there's no annulus crossing probabilities for SLE, so it is immediately like true for any SLE kappa. because this probability decays as power law of epsilon, and then we can use Fourier controlling to show. And the second part, this is also, although it looks a very believable property, it still takes some, at least it takes some pages to prove it. And also, one thing that we are still not completely happy about it is that we use the reversibility in proving this result, which might not be completely necessary, because if we don't use reversibility, then we can claim that this result gives a new proof of reversibility of SLE, because but actually currently we do. So the idea of proving this is just we run the curve until it hits here, and we just look at balls that are attached to this curve.
You should use the other one.
Okay. So this is SLE, and so for example, we look at a slightly smaller ball and look at a bunch of balls that the curve intersects, and then we will need to show that the future part of this curve can't hit every of these balls that are on the curve. So then we need to map the thing out and say, then it becomes some small bits which are attached to the boundary of the upper half plane, and then this future, and their size are small, and etc. So this curve cannot hit every of it. And once we have this, then inside this ball we can find an even smaller ball that the curve doesn't hit, and so that it's much closer to this curve than the future part of the curve. And we use reversibility because then to say that then we can do it in the reverse direction, so the path doesn't hit this parted curve. But it seems to use a very strong result for showing this. So that's the main idea. Okay, so I don't want to go to more details because it's Okay, so thank you for your attention.
So what you're saying is that if you wouldn't need reversibility there, then it would provide a proof of the reversibility based still on the zipper.
Yes, based
on the fact that there's the downward zipper. I mean that there is the zipper exists somehow. I mean that zipping down works. Then you can zip up again, and then you can say that.
Actually, you can zip in one direction or zip in the other direction.
And then it doesn't mean that therefore the whole thing is unique.
Given the Gaussian free field, the two surfaces, there is a unique way to weld it, so it's the same curve. Would be in one direction or the other. Well, it gives the reversibility, already gives the reversibility of this coupling.
Yeah.
But doesn't.
So what you get there is the reversibility also of the. I mean, I remember that there was a reversibility of the welding by Dapping and Stefan or something. That related to that would follow also.
So what result do they prove?
Stefan and Stefan, they proved that it's we only zip up the real line, so you get a random slit on the sphere. I think probably it's different than in the
It's
causal
a different
case.
one. Okay.
Mhm.
Yeah. Yeah, it's just a difference with this making trees. It doesn't depend on the direction.
Are there other questions? Just one question. What happens for kappa equal 4? What do you need to do for kappa equal 4?
So for kappa equal to 4, it also follows from this general result that because SLE4 satisfy H1 and H2, so if you just look at the SLE statement, it just says if the curve and its image are both SLE, then this phi must be conformal everywhere. Yeah, actually here I always draw the curves as simple curves, but in fact they, of course, can be self-touching. They can, so it can be a bit like a carpet. Yeah.
Thank you.
Thank you.